improvements of Tungsten Fabric control plane component. The control plane of Tungsten Fabric is represented by two major modules, the router agent and controller. And today we will talk only about the router agent. The talk is separated into two parts, one about improvement of metadata service, and second about the excellent capabilities of Tungsten Fabric. The new version of metadata service has been added to the master branch of the Tungsten Fabric repository, and you can try it. The second direction is an active development now, but it should probably take a couple of months to prepare pull requests to the master branch. First, we will talk about the Tungsten Fabric metadata service and how to enable it over IPv6 protocol. Today, this service works only in IPv4 environment, which means that you need hybrid IPv4, IPv6 networks or some auxiliary networks to provide this net functionality for your cloud. However, the OpenStack metadata service, which is actually proxied by TF, already capable of working with IPv4 and IPv6 standards. You can find more information about the concept of metadata on next resources. They are all listed on slide, as well as you can find information or links into TF spec, which was merged previously to Tungsten Fabric spec repository. Main purpose of metadata is injection of data, like settings, passwords, and so on, to virtual machines. And there are some drawbacks and benefits of this service, but we will not discuss these drawbacks or advantages. We will just consider one issue: how to make metadata service work with IPv6 protocol in Tungsten Fabric. Actually, Tungsten Fabric, this Tungsten Fabric service is a proxy. It relays messages between a virtual machine and Nova server, and general structure is presented here. It is simple, but it contains some intricate points. Wait a minute. You can imagine the router as a big pinball desk, and we need to talk a little about the router, because actually this plane is connected to metadata service. The complicated part of metadata service is organization of interaction between underlay and overlay networks. And actually, TF metadata service is based on NAT technology. Because metadata service belongs to link local service, it is expected to work on fresh virtual machines, while other TF services use link local, while other TF link local services use packet analysis module. TF metadata uses NAT. It needed because first we have to forward packets between underlay and overlay, and second, because it is necessary to obtain identification information for Nova. Last issue is solved using unique link local addresses from the range 169.254. These addresses are assigned to each virtual machine, and then they are used to obtain credentials for Nova server. However, with IPv6, we don't need this special type of addresses because this standard defines its own unique local addresses. Moreover, IPv6 net is not implemented in Tungsten Fabric. Therefore, if we want to avoid modification of kernel vRouter module, we have to find some different approach to forward packets between underlay and overlay first, and to obtain credentials for Nova server. Here on this slide, you can see a summary of Tungsten Fabric link local services. General idea of services such as DNS, DHCP, and ICP is to use PKT module. Each time when a virtual machine sends request for some information, TF agent intercepts this request, processes this request, and sends a reply back to virtual machine. And metadata service behaves in a different way. It is a proxy, and it uses NAT. This scheme is presented on the slide. We can walk it step by step. We see that virtual machine sends request to vRouter. vRouter sends requests. vRouter requests for flow between this virtual machine and address of metadata server. Agent replies with parameters of the flow, and this is actually a net. And this net is used by the router to send packet forward. Finally, this packet arrives to agent, and agent uses destination, not destination, source address from range 169.254. Agent uses this address to obtain UUID of VM and to send request to the Nova server. Okay, and if we want to solve the problem using IPv6 protocol, we can modify this scheme without employment of NAT6. VM sends request to metadata 6 server, which is located by address FE80. And when the router receives this request, it asks agent for flow. At this step, we can intercept this request. We can obtain a link local address of IPv6 link local address of virtual machine, and we can find its UUID and other necessary information. Then agent is able to advertise all necessary rules and establishes the flow. After that, steps are similar to previous slide. The router sends message to agent, and then agent sends requests to Nova. Implementation of this feature required to change several layers of Tungsten Fabric. So measure changes was in L4 and L3, but there was a small change in L2 in the router. We will discuss it later. Here is a full list of changes, and nowadays the router doesn't allow to pass IPv6 packages from underlay to overlay. So it is necessary to enable this feature, and this is implemented using just one line of source code, so it doesn't affect the overall behavior. Okay, here is just a snapshot of source code to intercept incoming request. You can see that each incoming request is analyzed in PKT model. If we find that destination address is equal to address of service server, then we try to advertise all necessary routes and prepare credentials for Nova server. All source code was committed to master branch. It is possible to download latest version. It is possible to compile it and to try using Metadata 6 server. Here are steps to run Metadata 6. First of all, you have to enable IPv6 between underlay and overlay. To do that, you need to run to y into the parameters of module. I think this is more or less known operation for all advanced users of Linux. Second, you have to prepare virtual network with IPv6 subnet, and you have to create new IPv6 instance and link it with VMI. Tungsten Fabric doesn't allow to advertise and to work with IPv6 addresses for interfaces which were not enabled for IPv6. Okay, then you can start a virtual machine and curl IPv6 addresses or IPv6 addresses of metadata server. And finally, I summarized main 6 points which arise during usage of metadata server. So they are listed here on the slide. First of all, it is necessary to check that IPv6 link local address of the metadata server appears in the corresponding VRF table. It can be checked using TF-GUI. Then it is necessary to check that security groups of the connected interface allows incoming and outcoming packets. Then it is necessary to change connection from VMI with ping. And if link local addresses of the VM which do ping, if it's a link local address appears in the Fabric VRF, then interception works and metadata server is able to advertise routes. And finally, if it still doesn't work, it's necessary to check that corresponding vRouter option is turned on. So this option is VRForce IPv6 underlay. Okay, so and now some considerations about improvement of VXLAN capabilities. Actually, I'm very new to SDN, and I've been in this field for just about 1 year. So it looks like Tungsten Fabric is a highly specialized tables processor. We have a large table which is stored in controller. This table is copied several times when we have several controllers. And this table is distributed amongst agents. So you can see on the slide 3 agents, and each agent actually holds copy of the main table. And to perform link between these tables, we have records which corresponds to tunnel interfaces. They are depicted with light blue rectangles. And the route table uses tables from the agent, which are actually partitions of main table in controller to forward packets. To understand what can be improved in VXLAN and how it can be improved, we have to briefly speak about how these tables are organized to store routes, to store routing information. So at the highest layer, we have a virtual network, which contains everything what is needed to define a connectivity between virtual machines. It has access control list of IPAMs, and what is more important, it has a link to VRF table. And VRF table contains, or VRF entity contains several tables, INET L3 tables, INET IPv6 tables, and EVPN table. Actually, in Tungsten Fabric, EVPN table can hold type 2 and type 5 routes simultaneously, but usually the work is organized in a such way that EVPN table has only type 2 or only type 5 routes. And there are other tables, we will not speak about them today. Each routing table defines a list of records. These records are routes, and routes are characterized by their IP or MAC address and tools to find records. A route contains IP. If it's L3, it can contain MAC address if it is L2, and it has a list of paths. So how to reach this destination? Prefix identify routes. It is a sequence of bytes, and it is a 4-byte in case of IPv4, and it is a 16-byte sequence in case of IPv6 address. Path contains information to reach prefix within the route, and it has tools to manipulate this path. Within path, we have 3 entities. We have next hop, peer, and other entities such text list, security groups list. Next hop defines next destination of a packet to reach this prefix address from route. Next hops of Tungsten Fabric in general are similar to their definition, which can be found in Wikipedia, but they can hold some additional information. For example, we operate with 4 main types of next hops. Interface, it means that path points to interface of virtual machine. Tunnel, it means that path points to neighboring compute agent or neighboring router. VRF is a special type of next hop which allows to jump from one VRF to another. And composite is a next hop which allows to gather paths from several sources under umbrella of one route. And another one interesting concept which is used in Tungsten Fabric is peer. Peer shows origin, where a path originates from, or a purpose of this path. The most used peers are local VM peer for interfaces. BGP peer means path which was advertised using BGP protocol, and ECMP peer, which characterizes paths pointing to several virtual machines. Again, peer together with the next hop make up the path. A list of paths make up a route, and combination of peer type and next hop is unique within route. And if you add another path which has a next hop and path type equal to those that are contained in another route, then they will overwrite content of previous content of a route. A list of routes make up a route table, and route tables make up a VRF instance. And second concept, which is necessary, which is important for VXLAN, is route leaking. Route leaking actually is a procedure of route synchronization between two tables. So we just we establish the method how data from one table is copied into another table between different VRFs or within one VRF. And how finally VXLAN control plane is implemented in Tungsten Fabric. It is implemented by route leaking from bridge VRF into one routing or exchanging VRF. So several VRF instances are connected to logical router, and one of them is selected as routing VRF. Then, for example, one virtual machine connects to bridge VRF number 2. This connection creates interface path with corresponding route in bridge VRF. This information flows into VXLAN logical router. Finally, this results in appearance of interface route, appearance of route with interface path in routing VRF, and then this information is distributed amongst other bridge VRFs. This process is triggered by changes in bridge EVPN type 2. If you remember, each VRF in Tungsten Fabric contains several tables, and in bridge VRF we have EVPN type 2 tables and INET tables. Changes in EVPN type 2 tables lead to changes also in INET tables, and these changes propagate into EVPN type table of routing VRF, and this finally ends in advertisement of routes in INET table of routing VRF. This is how routes from bridge VRF breach VRF instances appear into routing VRF. But okay, if we use some analogy, we can envision each path as a basket with section. Each section is a combination of next hop and peer type. And we see that interface ECMP routes export into routing VRF with type local VM port, and then they leak into routing VRF INET table into EVPN routing peer type. And the same happens with BGP peer routes. This route corresponds to tunnels, external composites, and other entities. It means that in breach VRF we have a route, or we have a route in which all paths are separated. But in routing VRF in INET table, all paths are mixed in one route. And this leads to some problems. First of all, when we trigger route leaking process by changes in EVPN type 2 table, we exclude leaking of special types of IP, such as floating IP, allowed address pairs, BGP as a service, and so on. So the only type which can leak into routing VRF today is interface. Then there is some synchronization problem. For example, because if we go back to previous slide, for example, if interface path leaks into routing VRF for one IP prefix, and then if another path with tunnel next hop, if it leaks after interface, it will rewrite our path. So in the current implementation of VXLAN of Tungsten Fabric, the latest leaked route is advertised in INET table. You can check it by using, for example, R2011 version of Tungsten Fabric. You can create several VMA and try to connect them to several computes and check what happens. And such a route leaking scheme doesn't allow to support ECMP routes. So they are not supported here fully. After some analysis of how it all works in Tungsten Fabric, we came to idea that it's necessary to change the scheme. First of all, changes should be triggered. Route leaking process should be triggered by changes in INET table, not in EVPN type 2 table. And second, we have to separate different peers in route leaking process. It is depicted here. Now interface routes leak into local VM port peers in EVPN type 5 route, and then they leak into VRF INET routes with with the same type of peer. And the same situation happens for tunnels and which has BGP peer, BGP peer type. They link into routing VRF table using different mechanism, and now we can have several paths with different next hop or with different peer type within one route. So there are no problems with synchronization now, and there are no problems with ECMP. This new version of algorithm actually has been developed, and it's on testing stage. Preliminary version allows to link FIP, AAP, and BGP as a service routes. This is absolutely new feature for Tungsten Fabric. And today I'm performing refactoring of the code. And next stage should be unit tests and functional tests. So finally, I would like to express my gratitude to my colleagues, to Yuri Konovalov for his ideas and overall supervision, to Andrei Pavlov for his assistance with CI, to my colleagues for valuable conversation, to Sayali Main, to Casey, to Nick Dave for organizational support, and to all participants of this session. A new version of Tungsten Fabric metadata service allows injection of data into virtual machine, pure IPv6 networks. Moreover, this approach can be reused for custom TF-Link local services that are still IPv4. And the new algorithm of route linking was proposed. And this algorithm allows supporting of floating IP, BGP as a service, and ECMP routes. Okay, I think that's all. Thank you. Maybe I lost. Looks like I lost my mouse. Okay. Do you have any questions? So no questions. So it looks like there are no questions, and we can stop this presentation. Oh, I don't know. Maybe we have to go for next presentation. Casey?
Sorry, I was talking away on mute. Well, we could just pause until the next presentation, just to keep to the schedule.